Welcome to another TA session of the NPTEL course, Mathematical Aspects of Biomedical Electronic System Design. So, in this session, we will be discussing about the mechanical modeling or mathematical modeling of mechanical properties of tissues and its applications in biomedical engineering. So, why characterize or why mechanically model the tissues and what is its importance? So, that's a key question that you might be having. So, why it is important? So, we know that human beings or even animals can have different diseases, and these diseases will cause the change in the human body or the tissues as such. So, from one pathology to another pathology, from a normal condition to an abnormal or cancerous condition, actually the properties of tissue changes, and the changes in properties can be mechanical, electrical, or several other different properties altogether. So, in today's session we try to understand the changes in mechanical properties and how we can actually model them, so that we can use these models to understand the tissue properties better, so as to invent or discover new treatment opportunities or the therapeutic applications, or even for diagnosing different tissue conditions. So, as a simple example, say a person riding on a motorcycle and hits a car or meets with an accident and undergoes a brain injury or a head injury. So, to prevent this, we have been implementing several methods. Okay, in case of a bike accident, we implement helmets, but in case of a car accident, we enforce seat belts. So, to prevent several injuries happening to human body during an accident. So, how do we come up with solutions like helmets? Okay, what should be the property of helmet so that it will be comfortable to a human to wear, or what is the properties of a helmet that will enable it to absorb the energy once the person hits the floor, or what should be the force at which an airbag opens up to prevent damage to the chest when an accident happens in a car. So, all these things actually takes into consideration the mechanical properties of our human body, how much stress our bones can survive, or how much the force that our tissues can survive without getting damages. Similarly, when it comes to cancer, the necrosis and all other different properties or phenomena actually causes changes in different properties, including mechanical properties of the tissue. And similarly, we also use mechanical properties or mechanical characterization when it comes to ultrasound imaging. So, there is a lot of forms of ultrasound imaging now, like Doppler imaging, B mode imaging. So, all these types of imaging that have been used currently all are based on mechanical properties of the tissue in one way or the other. So, also when we come to wearable technologies, okay, you are designing a smart band. So, what should be the appropriate comfort, the material property of that band, like a rubbery material or a metallic band, which actually gives you the most comfort. So, for all this, we actually analyze the mechanical properties of the tissues, and it is essential to mathematically model them when it comes to simulating the actual conditions in a FEM tool, or when it comes to designing a product. So, that is why we in this course discuss about the mathematical modeling of mechanical characteristics of tissues. So, say we have different models that have been put forth by different scientists over the period of time. Maybe after the mechanical properties of tissues might have been explored for last 50 years, 60 years extensively, and we have a lot of models that have been proposed, mathematical models that have been proposed to categorize the tissues. Okay. And before going deep into which are the specific models that have been used for tissues, we have to go through some basic understanding of different mechanical properties that we might discuss across this lecture. So, as you can see, the tissue models that have been proposed usually are viscous or elastic. We can broadly categorize them into viscous properties as well as elastic properties. Now, what is the difference between both of this? Is that one, this rate dependent properties are basically nothing but, okay, if you apply a force at some specific rate, the tissue will behave like this, okay. And the elastic properties is more like, okay, if you apply this much displacement, or you compress the tissue this much, or you pull the tissue this much, okay, then what is the behavior of tissue. So, this is two different things that we have to understand towards developing these models, and the combination of several of these models have also been there, such as viscoelastic model, where the tissue have been modeled to compensate for both these behaviors together, as well as hyperelastic models, and various scientists have devised their own models, okay. So, now coming to basic understanding of some material properties before going towards tissues, we can actually understand what are the basic terms that we might use during this session, okay. Now, before going to even tissues, we will consider the properties of metals and polymers such as rubber, in order to actually understand how these are similar to tissues, and why we can use these polymers or other materials as analogous to tissues. So, rather than explaining everything based on tissues, we can go for materials that are very similar to tissues, such as rubber, in order to characterize the tissues, okay. Now, you might already know what elasticity means. So, elasticity is basically like you say, okay, we have an elastic band or a rubber band which we can pull and it goes back to its normal shape. So, if we pull it like this with a force F, it stretches to a longer length, okay, and when you release this force, it goes back to its initial size. So, you say, okay, this material is elastic. So, basically elasticity is the ability of material to resist a deforming force, and once this deforming force is removed, its ability to come back to its original shape and size. That is what elasticity is referred to as. Now, to this as okay, even though we might term this as elasticity or elastic properties of the tissue, we need to quantify it somehow, or for any material we need to quantify what exactly elasticity means. That is why people have devised or brought up terms such as elastic limit and elastic modulus, okay. And what exactly this means? So, this means that elastic limit is a maximum stress that the material can bear before it undergoes permanent deformation. That means, if you apply some force F, okay, the material stretches and it comes back to its stretches like this, and it comes back to its initial form like this when you remove the force. But beyond a point, okay, if beyond a force say F max, what happens is it will deform such that it will not come back to its previous shape. So, it actually kind of gets damaged. So, this is what actually is meant by the elastic limit, and we through different material characterization steps, we have found this elastic limit for several materials. And say, as you might already know, okay, the elastic limits of metal is significantly higher than that of materials like rubber and other polymers, most polymers, okay. Now, the next parameter, okay, so elastic limit is basically nothing but, okay, the maximum stress that you can apply, so that the material does not get permanently damaged, you can say it like that. Now, there is another term that we say is the elastic modulus. So, elastic modulus is nothing but the ratio of stress and strain. So, when you apply a force F, Okay. So, when you apply a force F on a block, okay, and of cross sectional area of A, okay, it experiences a stress. This we might have studied in school itself. So, this stress sigma is equal to F by A. Okay. Now, what is strain? This basically when we apply this force, an elongation happens by say amount delta L. Okay, this is total displacement on both sides, okay, together. If it is delta L and the original length was L, okay, then the strain epsilon can be expressed as delta L by L. So, this is the strain basically. Now, so these two parameters, the stress and strain, and the ratio of it is known as elastic modulus. So, you can see the graph over here. Okay. So, you can see a elastomer or something like a rubber. Okay. When you stretch it, okay, if it was the length was like this and you stretch it this much, okay, the stress developed in this rubber will be comparatively less than if you are stretching a same metal. So, if you stretch a metal to the same extension as this rubber, the stress developed in the metal or a material of that much high stiffness will be way higher. Okay. So, the elastic modulus of metal is very much higher than rubber. Okay. Now, the deformation of material can be of two types, okay, and elastic and plastic. So, the elastic deformation is basically what happens within this elastic limit, and the permanent deformation when you cross the elastic limit is referred to as plastic deformation. Okay. Now, the materials when we apply the force, the deformation happens. Okay. So, if I draw a cube, consider this as a cube and you apply a force. Okay. Now, when the cube gets stretched in this direction, there will, if it is a metal, what happens is there will be a reduction in volume or a reduction in width as well as breadth in these two directions. It is because the volume of the metal does not change much. That is like when it gets stretched, the compensation happens from the other two sides. So, that the quantification of that effect is often referred to as Poisson's ratio. So, there is a change in volume associated with the stretching, okay, and this is referred to as a Poisson's ratio of the material. Now, how the deformation happens can be explained using two theories, okay, and one is the molecular mechanics. It is not two theories, it is two principles that cause maybe say metals and rubber or the elastic materials to show different behaviors, and this can be classified as molecular mechanisms and phenomenal mechanisms. Okay. Now, say for this I will just show two take two different cases, one being the behavior of metals and one being the behavior of rubber. Okay. Now, rubber or polymer or polymers, a few of the polymers. Okay. Now, how these two materials are different. So, for this we are just doing going through a simple experiment where we have a rubber, maybe a rubber band or a rubber material here, and then you hang a weight to it of weight W. So, you will very intuitively understand that okay, when you apply this weight W, it stretches, say it stretches by some distance length. Now, if you apply some heat to this rubber when it is already under a weight W, you can notice that okay, the rubber will shrink back, maybe not to its initial position, but at least it will shrink back to a reduced length. Okay. And this is called as Gauss-Joule effect. Gauss-Joule effect. Okay. Okay. So, in case of metal, if we do the same experiment, you can see that okay, the metal was there, then you applied a weight W, and when you heat it, it will again elongate. And how exactly does this happen? Okay, both are materials, both were subjected to the same weight, and then you apply just temperature, and the behavior totally changed. And how does this actually happen? And this can be explained based on thermodynamics. Okay. So, this F dx, or you might already know that it is the work or the work done. Okay. This work done can be represented by the changes in both internal energy du as well as change in entropy of the system, entropy and internal energy. Okay. Now, said this, how, but still how does it actually cause this material behavior in rubber as well as metal? How does this change happens? That is because of a specific effect that happens in polymers or rubber, that is adiabatic stretching and strain induced crystallization. Okay. Now, let us come here. Okay. So, the internal structure of a metal might be like this. Okay, say there is a metal lattice like this, where these are say metal atoms. Okay. Now, this is very microscopic view. So, if this was a metal block and you were applying force like this, so what actually happens is these atoms which are in ionic interaction with the other atoms here undergoes deformation. So, if it was a say like a crystal structure like this, it might deform to something like this. Okay. So, as you can see, if this this atom deforms to something like this, okay, this atom and this atom moves in. So, you can see that there is a change in volume altogether. Okay. So, this change in volume is caused by this force, and this change in volume also causes change in internal energy of this metal, change in okay. Now, what the changes actually happens is in okay, the ionic bonds get distorted. So, what happens when you release the force, these ionic forces are strong enough to bring it back to its original shape. So, whatever force we applied here comes back to its initial state. This is what happens in case of metals. Now, in case of polymers like rubber, what happens is it is a polymer. So, it is a combination of monomers that is within it, and all these monomers are held together by covalent bonds. Okay. And these monomers can be like this, each monomer can be like oriented in different fashions. Okay. And maybe some carbon based carbon bonds or something like that will be there, and the angle between this carbon bonds might be say restricted to say 109 degree. Okay. So, when you apply the force, since the covalent bond is strong enough to maintain this 109 degrees, okay, the covalent bond will maintain the same angle, and if you apply more force, the covalent bond just breaks. Okay. So, it will cause say plastic deformation, permanent deformation. Okay. So, in most of the cases what just happens is this, if you stretch the rubber, the coiling as of the monomers that you have seen here will just stretch out to become straight. Okay. That is the change what actually happens in rubber, and when you leave it. So, this state can be referred to as amorphous state, and here it is more like a crystalline state. and the amorphous state are associated with huge entropy. And here the entropy is lower. So, most of the change when we stretch a metal, it contributes from the change in volume, which is there in internal energy change, while in when it comes to rubber, the stretching actually reduces to the coiling of the monomers reduced to stretching and causes strain induced unbending or uncoiling of this thing. So, basically what happens, the stretching causes strain crystallization. So, when it becomes crystalline from an amorphous state, basically the entropy reduces. Okay. So, most of the effect or the predominant effect that comes into the work done of a rubber material or a polymer when we apply and release is basically due to the change in entropy. Of course, there is some change in volume, but still most of the effect comes from the entropy change. That is why when we apply the temperature, the rubber, since the entropy term or the change in entropy term is significant, okay, and if the temperature we increase it, it actually reduces the work done. And in the case of metal, since du is the predominant one and the volume change is significant, it will dominate over the work done and which will cause the elongation of the material. Okay. Now, considering all these things, okay, now we come to the viscoelastic behavior of the tissue. So, why did I discuss all these things of the rubber as well as metal? To tell you that, okay, a material like you could have a basic understanding like, okay, the rubber is very much similar to tissue when you feel it. Okay. And it is true that the mechanical properties of a rubber or a polymer is very much similar to that of a tissue in many ways. So, these properties of the tissue can is always most commonly represented by the characteristics of polymers itself. So, whenever scientists try to explore the mechanical properties of tissue, it is always very tightly aligned with the properties or characteristics of polymers in general. So, the methods used to characterize the tissue are very much similar to the methods used to characterize the polymers. Okay. And this is why we discussed all these behaviors of rubber so far. Okay. Now, so this is the basic idea that I wanted to give. Okay. And the conformation change that we discussed previously in the materials can the rate of conformation change can be expressed using this Arrhenius expression as shown in here. Okay. Now, coming back to the viscoelastic regime or what are the viscoelastic properties of tissue, you can see here. Okay. So, now consider we have a rubber and we are pulling it apart very slowly, or a tissue that we are pulling it up very slowly, and there is another same tissue we are pulling it fast. Okay. And you can see that its behavior totally changes depending on the rate at which you pull it. Okay. And similarly, when it comes to the temperature that we discussed previously, okay, the change in temperature causes different behaviors in the tissue or the polymer based on the thermodynamic principle that we discussed earlier. You can see here there is a plot of the rate of deformation versus temperature, and you can see that as temperature decreases, the slope or the rate of reaction increases quickly. Okay. Now, if you think about it, okay, you take a rubber band or something, you can try this simple experiment in your house. Even the other I have told here, the stretching and unstretching of rubber, you can actually see this with a simple experiment at your house. Okay. You can take a rubber band, okay, a usual rubber band or a rubber block, okay. You can freeze it. You can freeze it, and when in a refrigerator or something, and you will find that the rubber actually becomes brittle and you can just break it. Okay. So, take just a rubber band, keep it in a freezer and freeze it at some degree Celsius, and you will see that when you break it, you will see a coiled kind of behavior in the cross section of the rubber band, and which is actually feasibly visible. And in the another rubber band, you take it, you stretch it, okay, stretch it using something and again freeze it, and when you break it, you will see very aligned structure. Okay. So, this basically shows, okay, the orientation change or the uncoiling of rubber or the these kind of materials. Now, talking about this, so the temperature actually plays a significant role in the mechanical behavior of polymers like rubber as well as even for tissues. Okay. And there is a temperature that is referred to as glass transition temperature. Okay. And this glass transition temperature is a very important temperature. Okay. And if you heat the material or the polymer beyond, even this applies true for most materials, even glass or materials. Okay. What happens is when you heat it above its glass transition temperature, okay, it becomes rubbery or it becomes more elastic. Okay. And if the temperature is reduced well below the glass transition temperature, it becomes brittle, and you might be already able to understand why this happens based on the previous thermodynamic explanation that we have already gone through. Okay. Now, let us come back to material characterization or material characterization of human tissues. I have shown here an example of a characterization of brain tissues. Okay. So, a brain tissue was cut into a diameter of 8 mm in this research work that I have cited here. Okay. And they are keeping it between two plates, as you can see here. So, what are they trying to do? Okay. So, the materials have been characterized using different methods like say tension test, compression, okay, then maybe fatigue test. So, shear test. A lot of tests have been done. Okay. In tension test, a material will be pulled to its to understand its and once we pull it, we plot the stress versus strain, okay, and to see what is the elastic modulus, elastic limit, what is the elastic modulus, all these things. And same for the compression, you apply a force to compress the tissue or the material to know the behavior. Okay. You load it and unload it at very high rates to understand the fatigue. You apply the load in an angular way to understand the shear behavior of the material. So, all these tests have been done a lot, but when it comes to tissues, the most important characterization that people do is the creep test, relaxation test and the dynamic or sinusoidal loading test. Okay. So, why these tests are important to all these tests that we have already discussed like tension, compression, all this can be done, always. Okay. And these are very much similar to any other material, but when it comes to specific case of tissues, this is that's when it actually becomes important to do this creep test, stress relaxation test and dynamic loading. And you will understand over the course of a few slides that comes down that okay, why it is actually important. So, first we will talk about the creep test. Okay. So, now we will talk about the creep test or the creep behavior of the tissue. So, you can see a graph over here when you apply a strain, okay, and you plot it against time. So, as you can see, there are 1, 2, 3 plots here, and I am naming them as okay. So, what basically is creep, that we will explain first. Okay, now you apply stress on a material. Okay, you apply some force on a material. Okay, initially you can apply a force on the tissue, okay, at a slower rate, slowly you pull it, or you apply a force slowly, then you increase the speed at which you apply the force. Okay, the speed at which, or the rate at which you apply the load or the F. If you change this, that is like you apply force faster, if you apply the force slower, you will actually get different strains when it comes to this kind of materials such as tissues or polymers. Okay, and this is known as creep of the material, or it is basically the time dependent strain or that rate dependent strain of the material, and hence the strain epsilon, okay, can be represented as a function of time, and this delta here is the tissue displacement, since also displacement changes with time, and this is the initial length L0. So, basically the strain can be expressed as a function of time in this case. Okay. And you can see here, say if the stress in this case. So, what basically what we can what we usually do to do a creep test is, you keep a tissue, you almost instantaneously apply a force F. Okay. So, the stress in this tissue will become, say something like a sigma 0. Okay. And this is what happens in a creep test basically. Now, if you apply double the load, that is 2 sigma 0 and the 4 sigma 0, you can see that the strain observed will also get doubled, like from sigma 0 to 2 sigma 0, the strain rate at every instant of time will be almost double. Okay. If you make it 4 times the initial value, it will become 4 times. So, this is what creep means, that is when you apply different if you apply different loading rates to the tissue, its behavior changes. Okay. And this is called as creep. Okay. So, now okay, creep is understandable. Okay, there is a strain that is a function of time, and since the displacement is a function of time. Now, you need to say, okay, quantify it or normalize it with respect to the stress that you apply. For example, okay, the strain correspond to the strain that correspond to sigma 0 force and the strain that correspond to 2 sigma 0 force, we need to actually compare them somehow. Okay, what is the actual effect of this? So, that is why we have brought in a term known as creep compliance. Okay. And this is basically nothing but the ratio of the strain, that is a function of time, with respect to the stress that is being applied. Okay. And you could just see that if you apply or if you double the stress, what actually happens is, from the basic say if this was epsilon 1 of t, okay, and if it was epsilon 1 of t for sigma 0, when you make it 2 sigma 0, the stress when you double it, or the initial stress, the stress that you initially applied gets doubled, what happens is the strain also gets doubled. Okay. So, that is the basic understanding. Now, we can also do what is like to take the plot of this creep compliance against logarithmic of time. You can see the variation from the glassy state to the rubbery state, okay, of the material when the when we change over the period of time. Okay. Now, let us talk about the next characterization method, that is known as the stress relaxation. Okay. Now, we discussed that you apply a specific amount of stress to a material at different rates and you will get different strain rates. And similarly, the vice versa of this is basically you apply different strain, or initially you, this was the tissue, you compressed it to say x distance, and in the next case you compressed it to 2x distance and you apply it to 3x distance. Now, what happens is each different displacements also causes different stress in the materials. Okay. So, each time if the material is linear elastic, what happens is when you double the strain that you have given, or if you double the displacement that you have given, the stress also just gets double when it comes to a linear elastic material, okay, or linear behavior of the material. So, what happens is now after applying this displacement, you just keep on measuring what is the stress in the material. You will understand that over the period of time the stress in the material comes down. That means the tissue or the material relaxes, okay, or the stress reduces. So, this is called as the stress relaxation, okay, and this is referred to as you say, or we have quantified this by using the term relaxation modulus, okay, and this you are already familiar, okay. The elastic modulus of the material can be given by stress by strain. So, it is the same thing, but just that the variation with respect to time is also important here. So, the initial strain that you apply is epsilon 0 and the relaxation modulus as a function of time can be plotted. Okay. So, this is the basic understanding of two different processes, stress relaxation as well as creep. Now, both creep and relaxation are both manifestations of the same molecular mechanisms, but you will feel that even these two are related. Okay. See basically that CRP was given as epsilon of t by sigma 0 and E relative of time is given by sigma of t by epsilon 0. Okay. Both are very much similar, like you might feel that this CRP is equal to 1 by say E relative. Okay. They might be dimensionally same, but effect wise they are not the same. Okay. And the rate at which the relaxation happens compared to the stabilization of creep is actually faster in case of stress relaxation. Okay. So, that is there is difference between both, one is not the reciprocal of the other. Now, both these characterization methods that we have discussed so far, like the creep as well as stress relaxation, as you can easily see, you can see that they need time. Okay. So, either you apply some stress and wait for it to get the behavior, or you apply some strain already and try wait for it to give some results. Okay. So, you need some time to characterize the materials. So, basically this time where depending on the material it actually changes, maybe from minutes to hours or to days, but in our daily world application or to understand the behavior we do not have that much time. That is why we go towards dynamic loading of the material. In dynamic loading what we do is we very quickly apply force, like at an instant we stretch the material and another instant we compress the material, and we repeat this for very long time. Or so, this is one form of dynamic test. So, there are various ways you can do it. Maybe you can apply a sinusoidal. Okay. So, this is the strain with as a function of time. you can apply a sinusoidal form, waveform kind of strain, or what you can do is you can just give a step kind of response or the strain. So, all these things we can try it out, and these methods can also give us similar results or similar information as we can get through creep as well as stress relaxation test. Okay. So, now let us see if we can try an example with this. Okay. So, if I apply a strain as a function of time which is sinusoidal in nature. Okay. Okay. So, this is a harmonic kind of strain that we are applying. Okay. So, basically like this we are applying. Now, this is the peak strain that we apply. Okay. Now, it is observed that the stress that is developed in the material, okay, sigma of t, okay, is equal to sigma 0 cos omega t plus delta, where delta is a lag. It is similar, very much similar to the electrically when we have a resistor and a capacitor, or a resistor and a inductor. So, we know that okay, when we apply the current or when we apply a potential between these two, there can be a lag or lead of current and potential. Similar to that, in case of mechanical dynamic loading, there will the stress actually lags the strain that we apply by a amount of delta. Okay. So, this expression can also be written in a complex form, that is sigma star is equal to say sigma star dash So, if I represent okay, this generated stress as a function, okay, as a complex function, okay, and which is having a real as well as imaginary part, which are which have a phase of 90 degree apart. We can represent the same stress generated in this form. Okay. So, if we have this thing, so if we apply epsilon, so there can be a stress with a lag of delta. This is the imaginary part and this is the real part. We move towards with a angular frequency of omega, okay, and the tan delta can be represented, or the phase in form of tan delta can be represented as sigma 0 double dash by sigma 0 dash, and also you can say the magnitude of this complex stress function as sigma 0 itself is equal to root of sigma 0 dash the whole square plus sigma 0 double dash the whole square. Okay. So, basically what it means is, okay, the sigma 0 dash is basically nothing but sigma 0 cos delta and sigma 0 double dash is equal to sigma 0 sin delta. Okay. So, I guess you might have understood this part. Okay. Now, so basically the stress function can be grouped as a real part as well as imaginary part, or a so the stress is basically categorized into two different parts. Okay. And so converting this stress into the modulus or elastic modulus that we discussed earlier, we can write it as, okay, the real part of modulus, okay, is given by sigma 0 dash by epsilon 0, and the imaginary part can be said as and 0 by epsilon 0. Okay. Now, so this is the rationale behind bringing these two apart, like the complex part as well as, or the imaginary part as well as the real part of the stress function will be understood after a little bit later. Okay. So, now you understood, okay, there will be a real part as well as imaginary part for the modulus also. Now, why this kind of a representation is good, or why do we do this? Okay, this we can tell based on a quantity known as strain energy. Okay. So, this is very much similar to the work done that we discussed earlier in kind of thermodynamics. So, it is basically nothing but when you apply a strain, so some sort of energy is stored within the material. Okay. And this strain energy, say W, can be represented by integral of. Okay. So, this stress generated in the material with respect to the strain that we apply. So, when we take the integral of this sigma d d for the entire cycle of dynamic loading, we will know the strain energy stored in the material during the cycle. So, we will do the same for this dynamic loading that we discussed so far. So, W is equal to, okay, we can also represent this as, I am just adding dt on numerator and denominator. Okay. Now, this sigma we can represent it as two terms, right. So, I am just grouping them apart. Okay. For a single cycle, 2 pi omega the period, so this is the real part. Okay. When you integrate this, you will understand that this entire real part, this is the imaginary part. Okay, this entire real part becomes 0. Okay, you know this mathematically, and this term comes out to be pi into sigma 0 double dash epsilon 0. So, you will see that, okay, so during the entire cycle, the energy stored by the real part of the stress is actually 0. That means, whatever force that we applied or whatever stress that we applied, which caused an energy change or storing of energy, the real part of stress actually became 0 over a complete cycle. That is, whatever energy that was given in was given out once the cycle was complete. But at the same time, the imaginary part, okay, there is something that remains. That means, there is an energy loss associated with the dynamic loading. That is, whenever you apply a load or a loading cycle, there will be some amount of energy lost, and this energy can be lost as heat. Okay. So, there is the behavior of tissue or material where some part of the energy that was transferred during this dynamic loading cycle, that is being lost. Okay. That is usually represented by the imaginary part or the loss part. That is why we actually represent this the stress as well as strain relationship in case of dynamic loading and the lag between them as a complex function, so that we will actually understand what is its actual significance. Okay. Now, let us talk about, so now you might have understood the basic understanding of dynamic loading. Okay. Now, we move towards the different models that we use for this kind of applications. Okay. So, basically you know Hooke's law, okay, where force is F is equal to kx, where k is the spring constant. So, when you apply a force on a spring, okay, the spring can be better represented like this, because we are going to use that kind of a terminology later on, of a stiffness k, and when you apply a force, it displaces by a distance x. So, this is basically what our expressions for Hooke's law is. Now, the same expression analogous to F is equal to kx, we can say sigma is equal to k into epsilon. These are very analogous. Okay, instead of force we have stress, and instead of displacement we have strain. Okay, and this can be represented using a usual spring itself. Okay, so any material can be can be represented as a combination of springs as well as something that we call as a, this is spring, as well as something called as a dashpot. So, dashpot or a, okay, like a damper is, this is very this kind of a mechanism is always used in electrical models also. Okay, so you might be familiar with that during the previous lectures. Okay, so the dashpot, what actually does is, it doesn't consider anything relevant to the strain, but it is more concerned towards strain rate. Okay, so it is basically more like a damper. So, if you apply the force slowly, okay, if you apply force at a slower rate, the resistance that it will give is also slow. If you apply a very fast rate, then the damper will give you a higher resistance. So, in this case, the stress can be represented as eta into epsilon dot, okay, where epsilon dot is nothing but the strain rate. So, a dashpot is an element where it is the stress is dependent upon the strain rate, and instead of the stiffness k that we discussed, earlier, in a dashpot we define viscosity. So, now you understand maybe like, okay, the material or the tissue or the rubber or any other polymer can have the stiffness or elastic properties as well as the viscosity or the strain rate dependent behavior. Okay. So, combining this kind of elements, Maxwell proposed the Maxwell model, that he said that, okay, we can say that the materials can be a combination of a spring and a dashpot in series. Okay. So, whatever force that you apply the same force on both the elements. Okay. So, the so if this is spring and this is the dashpot, the stress in spring is same as the stress in dashpot. Okay. So, we call it as sigma only. Okay. And the total stretch that happens when you apply a force, okay, the total force that you apply, and that when you apply that force, the total strain that will be caused will be sum of the strains in spring and that in dashpot. Okay. So, that is what actually is the Maxwell model. Okay. So, this is why as you have seen earlier, okay, the material will have a plot of the varying, say, sigma versus time. Then why does it relax? Okay. Or when you plot the creep, okay, that is epsilon versus time, why there is a change with respect to time. This is explained by the presence of the dashpot there. So, the dashpot actually is affected by the strain rate, and that is why the behavior change of the material changes with time. So, that is why Maxwell proposed this model with a spring as well as dashpot in series with each other. Okay. Now, from the previous expressions that we wrote already, okay, that is equal to sigma is equal to k epsilon 1 and sigma is equal to eta into epsilon dot, that is 2. We can say the since we also discussed that epsilon is equal to epsilon s plus epsilon d, we can say the strain rate of the total system, okay, can be represented as naught plus, correct. And so, this can also be written as sigma dot by k sigma by eta. Okay. Now, this is the stress rate in case of spring. Okay. Now, to better give an idea about the k as well as or the stiffness as well as viscosity of this model, there is a thing called as relaxation time. A unit or a parameter known as relaxation time is defined. Dou or tau is given by eta by k, which has same unit as time. Okay. So, maybe seconds or something or minute, depending on the unit that you take for for viscosity as well as stiffness. Okay. So, this relaxation time will come everywhere. Okay. So, if you just solve this, you will get k into epsilon dot is equal to sigma dot plus 1 by 2 into sigma. So, this expression that I have given here is known as the constitutive equation for Maxwell material. So, basically the stiffness as well as the viscosity which is included in this relaxation time and the different strain rates as well as stress rate in the material will be related in this as per the constitutive equation for the material. Okay. Now, okay, how is this significant? How does this be useful? Okay. So, for that I will just show an example. Okay. So, there is a material and okay, there was a material and you were loading it, okay, to a suddenly to a strain of epsilon 0. You strained it like this, okay, and you are keeping it like this. Now, you have seen stress relaxation. So, the stress will actually reduce with time, okay. The stress is reducing with time. So, the sigma of t actually decreases with time, correct. So, the same expression using this constitutive equation we will try to solve how it works. Okay. Now, in this case and in this kind of strain that we applied, you will know that after we apply the strain there is no more strain rate or we are not applying strain anymore or there is no change in strain after we apply the constant strain epsilon 0. So, what happens is the epsilon dot term actually becomes 0. Okay. So, whatever left out will be this will be sigma dot is equal to minus by tau, or this can also be written as d sigma by dt is equal to minus 1 by delta sigma, correct. Okay. And when we integrate it, okay, between the total change in stress with respect to total change in time, what we can do is so basically I am just rearranging it, separating the variables and integrating. It goes here. Okay. And when you solve it, you have 11 sigma minus sigma 0 is equal to minus t by tau, or the stress as a function of time can be given as sigma 0 into is raised to minus t by tau. Okay, so basically the relaxation that happens in case of a Maxwell model for the applied strain as shown in this case is exponentially decaying, or the stress that we applied initially, or the stress generated initially by a strain of epsilon 0 actually reduces with time exponentially. Okay, and this is the plot, and this relaxation time can be physically quantified as the time at which the stiffness of the material, the K, or the stiffness of the material reduced by 1 by E times, or K by E times. That is usually defined as the relaxation time as in most of the electrical analog cases. Okay. Now, so this is one of the most basic mechanical model that people have proposed over the time. So there were modifications of, but this model, or the Maxwell model, cannot actually exactly represent the case of the stretch of the polymers. The Maxwell model cannot actually show it properly. So that is why the standard linear solid model or standard Maxwell model of the expression was developed. Okay. So in this model was developed because most polymers do not exhibit the unrestricted flow as shown by the Maxwell model. Okay. So except for some materials like this silly putty or warm tar, most of the other materials do not actually follow the simple Maxwell model as we discussed. Okay. So it is very limited to the materials that we can say of. But when it comes to polymers that we discussed earlier, there is a lot of entanglements between the polymers. So it cannot exactly be represented by the simple Maxwell model. Okay. So that is why this model, a standard linear solid or SLS model, was proposed, where we have a resistor in parallel with the Maxwell model that we already discussed. Okay. So if this spring in series is having stiffness of K1 and the viscosity of the damper is eta, and we have the stiffness of the other spring, okay, the parallel spring is to be say Ke that I am showing as here, and we can model the same model, or the can do the same way as we have shown in the previous case. Now, in the previous case, what happened was, whatever stress was up, or the force that applied across this series of spring and damper created the same stress in both, but the elongation was the sum of both. But in this case, the stress will be distributed among the two arms of the model, correct, right? So the total stress in this case will be the stress across this individual spring sigma E plus that of the previous model that we already discussed in the Maxwell model, that is sigma m. Okay. Now, trying to solve this model using the previous approach will be actually little bit difficult. So we will approach the same problem or solving this model using the Laplace transform model, okay, or taking the Laplace of the same thing. Now, so how do we do that? So we start from the constitutive equation. Okay, and we take the Laplace of the same thing. So here this was the constitutive equation, and now in this specific case of this one, or the right side branch with the spring and dashpot in series, we can say the stiffness is K1. Okay, and when we take the Laplace of the differential or the change in stress strain, what we get is S into S into the change in strain, or the dash over the strain rate shows the Laplace transform of that same function. Okay. And okay, and if we solve for sigma m dash as we did in previous case, we will get so it is this we are approaching the same problem that we did previously, but using Laplace transform, so that we can do the combinations later on easily. Okay. So now if I try to find the stress here, and here also if we take the Laplace, okay, the total strain in Laplace domain can be given by okay, and okay. So basically this result can be represented as sigma dash is equal to some value E, okay, and into epsilon bar. So okay, and so it is more like the previous expression that we wrote. Okay. So and where this E or the epsilon can be is equal to K E plus, or basically it is nothing but this constant within the bracket. So you can actually this is basically a model parameter that relates to stress as well as strain in the Laplace domain. Okay. So this expression totally is known as the associated viscoelastic constitutive equation. Associated viscoelastic constitutive equation. Okay. So similar to this SLS model or the Maxwell model, various other models are there for the tissues that or the polymers that we know of. Okay. And so before winding up, we will just do one example with this case. Okay. So as we discussed earlier, we applied a strain with respect to time like this, like we applied a step of epsilon 0, right. Okay. So instead of that, this time we will say apply as a unit function. Okay. So I can write the function as epsilon t is equal to epsilon 0 u of t, where u of t is equal to 0 to 1 t time less than 0, time greater than 0. So if we apply a unit step function, okay, and the Laplace of this function will be 0 by s, correct. Okay. So the previous equation that we derived will become sigma 0 by epsilon equal to Ke by s plus K1 by s plus 1 plus tau. Okay. So now we can take the inverse Laplace of these terms to get what we will get sigma of t, or the stress in back in the function of time, by epsilon 0 is equal to K E plus K1 . So basically this expression you are very much similar. Okay. This expression is nothing but the expression for stress that you got for Maxwell expression. You might be remembering that. So when we derived it for Maxwell model, we got the expression, the stress as a function of time decays exponentially. Okay. So, it is the same plot, but what we have got now by offsetted by, so it is the previous one, but we have an offset of k. Okay. So, it is the, so this is how the modified function or modified Maxwell model or the standard Maxwell model actually changes from the previous Maxwell model that we have discussed. So, we have discussed a lot of things so far. So, starting from how we categorize different materials, what is the importance of characterizing materials mechanically, what are the difference between a metal and a polymer, and how these polymers are similar to the tissues, and how the polymer based models can be used for the applications for the tissue. So, we have discussed a lot of models. Similar to this Maxwell models, we have Kelvin model, okay, and the standard Kelvin model that is little bit more complex than the Kelvin model or the void model. So, we have a lot of models like this which are used to depict the mechanical properties of tissue using dynamic texting. So, depending on the tissue behavior, one model might fit better than the other model. Okay. So, different materials will have, or the different type of tissues even will have different correlation with different models. Okay. Disease tissue might be better fit using maybe a Maxwell model. I'm just telling, I mean not really, but maybe a normal tissue will be more towards SLS model. So, depending on the application, depending on the experimental data, we can use different types of models like this, and we can actually find the parameters Ke. So, once you do the experiment and you get a result like this, what you can do is you can fit this curve and obtain different values for Ke or K1, okay, so that these models can be used further for various simulation applications as well as designing various tools. Okay. So, I hope you found this lecture or this session useful. Thank you.